So in this situation here, we have a student who is trying to find out how long the ball that is dropped is in contact with this balance. And so he's devised a technique for doing that. And so let's put some of the data to and bring this thing to life here. So the first thing I'd like to talk about, though, before we do that, actually, is to talk a little bit about, we have now starting to develop a lot of tools for approaching different questions. And so we have different questions. We realize that there's, and this is where we're showing metacognition and thinking about our thinking and about what we're going to apply to a particular situation. So far in the course, we have learned kinematics. So we could put on our glasses and look at everything through the lens or the perspective of kinematics. We have also now learned about the two most important ideas in all of physics that drive everything, and that is the law of conservation of momentum and the law of conservation of energy. And so really, these two are the perspectives we are going to use very often to figure out complex phenomena. The law of conservation of energy, law of conservation of momentum. We may also use kinematics, how things descriptively, but really the causal elements are momentum and energy. And so when it comes to changes in momentum, what we're dealing with largely are collisions and interactions where there is changes in velocity. With energy, we have changes in velocity and changes in height involved. And so that's a way we could look at this problem and start to say, well, we can try to figure out everything we possibly can using kinematics. And we may reach a dead end, in which case we'd put on our momentum glasses and calculate everything we possibly can when it comes to momentum. Or we could do the same thing and calculate everything we would need to know in terms of energy. But keeping in mind that momentum is really all about changes in velocity, whereas the energy is changes in velocity and energy. And in truth, we may have problems that involves all three of these perspectives. But in other words, we don't have to know exactly how to do a problem when we start. We can systematically approach all of these. But knowing these distinctions between what energy might do for us and momentum might do for us versus kinematics could be important. So let's talk a little bit about this situation. We have a ball that's dropped from a certain height. And so what we know is it's going to have gravitational potential energy. And it's going to fall and its velocity is going to increase. And just before impact, all of that energy will become kinetic energy. We are told then that that height is 0.80 meters. And that afterward, the ball bounces and it goes up to a height of 0.6 meters. So it comes up to a height of about this, 0.60 meters. So the ball comes down, and when it ends up back at this new height, it has gravitational potential energy. And you can see that some of that potential energy will have been lost. Well, the velocity that the ball has to carry it up to this height comes from its kinetic energy. And so when we look at all the possible places, we have the trip down, the energy of the system, the mechanical energy, the potential, and the kinetic. All there is change between those. And once the ball leaves the pan, the kinetic becomes gravitational. So any loss in energy must have occurred during that interaction with the pan. And of course, during that collision, we can have sound energy, vibrational energy, and thermal energy. The ball and the pan itself will heat up. So that's where the energy is lost in that particular case. So we want to know, we're given the mass, and we're given the acceleration caused by gravity, so this is Earth. We want to know the speed of the ball when it strikes the scale pan. Well, that's a free fall situation. So we could use kinematics to solve this equation. We could find out how long it will take for it to fall and hit the ground, and then use that time to find the velocity. Or we could just start out using our conservation of energy. So we know the change in gravitational potential energy is going to be equal to the change in kinetic energy. And the change in potential energy is going to be mg delta z is going to equal 1/2 m delta v squared. Now we can see in this equation that there's mass on both sides, and those masses are the same mass. It's a mass of the ball. So in other words, what we're seeing is the velocity doesn't depend on the mass. Well, That's not surprising. Gravity acts on all objects equally, and they all accelerate at 10 meters per second squared. So going further to solve for v squared, we have delta v squared is going to equal 2g delta z, and therefore v is going to be the square root of 2g delta z. And then v is the square root of 2 times 10 times 0.8, which turns out to be 4.0 meters per second. And that is going to be the v, and it's going to be the delta v because v0 was 0. It's dropped from rest. So that is our speed when it hits the pan. And we know some energy is going to be lost. So now we are asked, what is the speed of the ball when it leaves the scale pan? Well, in the first situation, we looked at the potential energy converting into kinetic, and we have the kinetic energy turning into potential energy. Well, we can determine the potential energy it has, and then we will then know what the kinetic energy must have been. So it's interesting that the potential energy will allow us to determine the kinetic energy here, and it's also the potential energy that allows us to determine the kinetic energy after it starts to bounce. So we have the same fundamental relationship. Change in potential equals the change in kinetic. So we know from above that v is the square root of 2g delta z. So that is the square root of 2 times 10, and now the delta z is 0.6. And that velocity works out to be 3.464 meters per second. To two significant digits is 3.5 meters per second. And that is going to be the v when it leaves the plate. And that actually makes sense. The velocity should decrease because the energy is lost during the collision. So it should be less. And now we want the total change in momentum. Well, delta P is m delta V. And the mass is 0.20, we're given above. And delta V, well, this is, since we're now talking about V is velocity, and what we computed above were the speeds. So the final velocity, let's see, we make positive is up and negative is down. Well, the final velocity is up. And so we have 3.5 minus the velocity. We have a positive 3.5 meters per second upward. We have a minus 4.0 meters per second downward. So that's minus a negative 4.0. And that gives us 0.20 times 7.5 for an overall change of 1.5 kilogram meters per second, and that is going to be the overall change in momentum. Moving on to the second part, we know we've got a graph here, and this is what Miguel assumes is going on with the force with respect to time. So we have a graph, so we'll do some Oizerga. The origin looks like that is 0, 0. Y-axis is force. We have time. The intercept, it looks like there are two x-intercepts here and here. We can read force and time. The gradient is delta F over delta T, which is the rate of change in force. And the area is F times delta T, which we recognize as the impulse. And of course, impulse is equal to the change in momentum, is the average force times the change in time is m delta V. And we just computed in the previous question what the change in momentum is. We found it was 1.5. So we know the area under this graph should be 1.5 from the previous question. So what does the area represent? The next question, that's easy. The area represents the impulse, which is equal to the change in momentum. And now we're asked to find the contact time, delta T. Well, we know the impulse J is delta P is F bar delta T. And if we want delta t, then, well, delta t is going to be delta p over the average force. And the delta p we know is 1.5. Well, the average force in this case, the max is 50, the min is 0, so the average force is going to be 25. Average force is going to be 25, so 1.5 divided by 25 works out to be 0.060 seconds, and that is going to be the delta t. Now let's see if that number makes sense to us. The average velocity, if we draw the average force, that would trace out a rectangle. So this then is F bar, and this is delta t. And if we look at this, we can see that the area over here, this yellow area, is going to be equal and opposite to that yellow area. This yellow area is going to be equal and opposite, or is going to cancel out that other area. So if we fold those over, if we take this area and fold it down to here, and that area and fold it down to there, that area of that triangle will indeed be equal to the area of that rectangle. So now we're told Miguel drops another ball from the same height onto the scale pan. Same height, okay. So that means same height, it's going to have the same velocity. So we know it'll be 4.0 meters per second. It's made of a harder material. A harder material means that delta t will be less. The ball will deform less. And if we think about padding, of a boxing glove, of a pad, any kind of pad, we've spoken about that. What that does is it increases the time. So delta t will be less. We'll have, it will deform less, so we'll have a smaller delta t. So on the graph above, sketch the shape of the graph. So here's what we want to say. Delta t will be less. And we know that the change in momentum, because the velocity is the same, the change in momentum must be the same. The delta p will be the same. And that means the area will be the same. So if we go and draw this up top, what we can see then is that delta t will be less. So let's say that's our delta t. To get the same area, then, we must have a taller triangle. And now if we look at this a little more closely here, we could see then that this area up here should be equal to the area down here when we draw this triangle. And the area on that side should be equal to the change over here. And so we should draw that accordingly. Now, of course, according to my diagram, that given that change, I should probably have a taller force to get more area. But you get the idea. So the third thing we might say is that F max will be greater. And so we can show this in the graph. What we're showing by drawing this newfound curve like so is we are showing that delta t is less. We are showing that F max is more. And we are drawing it in such a way that the areas are equal. I like to also state these things in the space for the answer, what it is what I'm explicitly trying to show, these three things. And that is A2.